All right, welcome to lecture here. We're going to be continuing on with the stoichiometry that we started talking about last time. Okay, so we started talking about stoichiometry really last time. We talked about sort of a couple different sort of stoichiometry type problems. Um, Really, we have a basic stoichiometry problem. And remember that stoichiometry really is kind of using a balanced equation, using some type of information like either how much reactants you started with, how much products you started with, to basically figure out something based on the equation. A lot of times we figure out what is sometimes referred to as the theoretical yield. And the theoretical yield is really the maximum amount of product that you should produce in a reaction based on the equation and based on how much reactants that you start with. Again, if everything went perfect, nothing bad happened, no side reactions, you didn't lose anything along the way. That's really how much product that you should make. Now, in sort of basic stoichiometry problem, right? You can doesn't necessarily have to figure out products. You could figure out if you know how much product did you made. You could go the other way and figure out how much reactants you started with, and sort of back and forth. So in a traditional sort of stoichiometry problem or sort of a basic stoichiometry problem, you're really only given information about one thing in the equation, and you could use that information really to find out, other information from the equation. Now, really all stoichiometry is really just a conversion factor, and unlike going to like a table to figure out the conversion factor, we figure out the conversion factor by using the balanced equation. So it's always important to have a balanced equation. Um, and there's really four basic steps when you do a stoichiometry problem. Um, as a basic stoichiometry problem. The first one is that balanced equation. So nothing will work correct if you don't have a balanced equation. So you need to make sure that it is balanced. Then whatever they give you, and again, whatever units that may be in, a lot of times it is in grams, but it doesn't always have to be grams, but a good majority of the time it is in grams. You do need to convert those grams into moles. So usually that would require the periodic table and the molar mass to do so, to go from grams to moles. And once you do have it in moles, what you want to do is go to the equation. And again, that balance equation, find the two things you're interested in. And usually one thing is what they gave you. The other thing you're interested in is what you're trying to find, and find what is referred to as the mole to mole relationship. And the mole to mole relationship is really the stoichiometry part of the calculation. And it is nothing more than the actual coefficient that we have in the balance equation. So for example, up here in this equation, for every 1 mole of TiCl4, we do have to put in there 2 moles of magnesium. For every 2 moles of magnesium, we get out 2 moles of magnesium chloride. For every 2 moles of magnesium, we get out 1 mole of Ti. For every 1 mole Ti, we produce 2 moles of magnesium chloride. So really, those are conversion factors. They're equal to each other. And as we talked about yesterday, obviously, they're not equal to each other in terms of numbers. 2 and 1 doesn't equal each other, but they are equal to each other in terms of sort of proportion for that particular reaction in order to proceed correctly. That is sort of the ratio that you need. And because they're technically considered equalities, you could write really two conversion factors for either one. You can write, for example, 1 mole of TiCl4 over 2 moles of magnesium, or you could write 2 moles of magnesium over 1 mole TiCl4. So the sort of third step is to go to the equation, find that mole to mole relationship, and that will allow you to convert to what you're really interested in. And the fourth step is to basically, a lot of times, convert those moles into something else. So if the answer wants to be in grams, you again usually will have to use the molar mass on the back end there and calculate the grams. Or you may have to calculate some other unit. So there really is in a basic problem sort of 4 steps that you could do. And if you again just follow those steps sort of in order, you should end up with the right answer hopefully at the end. If anything's done for you, you just kind of continue on in the calculation, don't go backwards. or anything like that. Then we started talking about the idea of limiting reagents, and limiting reagents is the idea that in any reaction, there usually is always going to be a reactant that gets used up first. And when it does get used up first, that is what's known basically as the limiting reagent. And the other reagent in that case would be known as the excess reagent. And the excess reagent is the one that you have plenty of, so you're not running out of it. There's actually some of that reagent left over when the reaction is done. You'll actually have some of that still there and present. And the reason limiting reagents are important is because in order for a reaction to actually make products, you need both of the reactants, for example, or all the reactants. So in this example we're looking at, in order for us to make Ti and magnesium chloride, we need both of these guys really to react, right? So all those bonds could break and everything. So the importance of a limiting reagent or limiting reactant is it is really the one that determines how much product you could make, because as soon as you run out of that reagent, there's no possibility that you can make any more product. So it limits you, which is why it's called that. It limits really how much product that you can make. And when you do have a limiting reagent problem, the way that you usually could recognize it is you're given enough information to calculate the moles really of both reactants. So that's, again, usually a pretty key indicator that somewhere along the way you need to basically figure out how many moles of each of those guys and which one is the limiting reagent. And you then would use the limiting reagent to figure out how much product that you would make. Now, we talked about a couple different ways that you could do that, and there are a couple different ways that you can actually do that sort of calculation. And I sort of introduced maybe a new way for a lot of people, which are known as ICE tables. And again, if you plan on continuing on to 200B, that's pretty much all you do in every calculation is ICE tables. So you might thank me later, maybe not now, but later you might thank me when you get to that class that you've seen it before. But is a very sort of convenient way to figure out very common questions that are asked in limiting reagent problems, and you can figure out very quickly. So just let's review how that we did that one, and then we'll talk about some other ways, again, that you can solve these guys as well. So use this one, I think. All right. So in an ICE table, as we could kind of see on this one that we were working on, the first thing that we obviously did was we had a balanced equation. We converted everybody into moles. So we were given enough information for our two reactants basically to figure out the moles. And that's what you want to do here in our initial part of the table. For our purposes in this class, it's pretty safe to assume that you have nothing happening on the product side because the reaction hasn't taken place. Then the change part of the ICE table, usually represented by X, basically takes into account sort of the mole-to-mole relationship, the stoichiometry of the calculation when you do it. And we do need to find it. So we're assuming that this reaction is proceeding from reactants to products. So it's going from left to right. And what that means is the reactants should be decreasing with time, and the amount of product should be increasing with time as we're making it. And that's represented by the negatives on the change part here and the positive signs on the product side. Negative X, and when we do this, we do want to take in the coefficient, and for TiCl4, the coefficient is 1, so that's why it's just minus X. The coefficient here for magnesium is 2, which is why we have the 2x there for it. Ti's coefficient is 1, which is why there's only 1x, and 2 for the magnesium chloride, which is why the 2x. Now, those coefficients are extremely important in an ICE table to put in for the change part, because, again, that is really what does all the mole-to-mole relationship that you do sort of in a traditional sort of stoichiometry way. What we then do is basically just carry down the information to the equilibrium line, and in this case we had 1.3 times 10 to the 5 minus x, 4.65 times 10 to the 5 minus 2x, x, and 2x. after we do that, what we want to do is actually determine which one is the limiting reagent. And to do that, we're simply going to set each of the reactants equal to 0, which is what we did. And we're going to actually solve for X. And in the case here for the TiCl4 is 1.3 times 10 to the 5. In the case of the magnesium was 2.33 times 10 to the 5. The way you determine which one is the limiting reagent is the one that gives you the smaller X value. And in this case, it was the TiCl4 that gave you the smaller X value. That's how we knew that the TiCl4 was the limiting reagent. And by default, that means that the magnesium was the excess reagent. Once we figure out that this is our correct X value, that is the X value for everybody in the equilibrium line. So every X that you see basically in that ice table, that is what that value would be. And again, sort of the benefit of that again here is that this value is in moles, is you can very quickly find everything that you needed. So in the actual problem, we were interested in Ti, which is X. So we knew that X was 1.3 times 10 to the 5 moles. And then all we needed to do was simply use the molar mass to convert it into grams. And that would give us our theoretical for our Ti. We also saw that magnesium chloride, if we wanted to know that guy, is 2X. So we just need to take 2 times the X value. And that gave us how many moles of magnesium chloride was produced. And again, using a molar mass of magnesium chloride, we could get how many grams that was. We also can use it for a question that is usually asked in these things, which is how much excess reagents left over. And since the magnesium was our excess reagent, it was 4.65 times 10 to the 5 minus 2X. And again, if we put our X value into that, we saw that we had 2.1 times 10 to the 5 moles of magnesium left over. And then if we multiplied by the molar mass of magnesium, that would tell you how many grams was left over. So one of the nice things about sort of doing it this way is everything is sort of there. And with very short calculations, you can figure out pretty much any question that you may be asked without necessarily having to go all the way back to the beginning and maybe doing some separate calculations to figure out other things. So this is one way that you could do it. Another very popular way that people do limiting reagent problems is to simply do 2 separate calculations. One calculation, for example, in this case would be taking the TiCl4, converting it into moles, and figuring out how many grams of Ti it would produce, and then do a second calculation where you'd convert the magnesium into moles and figure out how many grams the magnesium would produce. And whichever one produces the smaller number of grams is both your theoretical yield and also your limiting reagent. So that's also a very popular way to sort of do these problems. And sort of the third popular way is, I think what I got on this slide, next slide here. Let's see here. A third way, which I think is what is done here. So we'll just look through this one here to kind of show you another way. And I'll sort of explain what's happening. So a third way is the same sort of beginning like everything else, which is you convert everybody to moles, which is what was done here. So this is just like what we did in the previous problem. We converted each of the starting guys into moles. And basically what you do in this sort of method is you pick one of the reagents, or reactants, and you do a calculation to decide if I want to use up all of that one reagent, how much of the other one do I need? And that's what this calculation on the bottom is here. Basically what I'm saying is if I want to use up 100% of my TiCl4, I'm going to figure out how much magnesium I need to put in there. And that's what this relationship is here. That 2-to-1 relationship comes from the equation. And basically what they did here is they figured out that if I want to use up 100% of my starting amount of TiCl4, I would need to put in there 2.6 times 10 to the 5 moles of magnesium. And what I do at that point is I compare how much was needed, which is this number, to how much I started with. And what we see is I needed in this calculation 2.6 times 10 to the 5 moles of magnesium. I started with 4.65 times 10 to the 5 moles of magnesium. I have enough. So I have enough. And because I do have enough, that tells me the magnesium is my excess reagent and the TiCl4 would be my limiting reagent by default. So in this sort of method, you could choose either reactant. I could have done the opposite calculation and figured out how much TiCl4 I would need to put in there to use up all the magnesium. It doesn't matter which one you choose. You could choose either one. And what I would find if I did the opposite calculation was basically the same result, that I would not have enough TiCl4 and it would still be my limiting reagent. So this is another way that you could do it. And then what we would do is pretty much what we did on everything else is we would come back to our limiting reagent and use that to figure out how much product that we would make. And that's what this calculation should be. Using our limiting reagent, we're going to figure out how much product that we produced. And as you can see, it pretty much is the same answer as we got last time, maybe slightly off with some rounding, but pretty close. And that again would be our theoretical yield. Right? And then we would obviously finish up the problem pretty much the same way as whichever way you choose. And we would divide our actual divided by our theoretical, and we would get our percentage, which again is the same percentage as we got in the other method. So those really are three sort of ways that are very commonly used to do limiting reagents. As I mentioned yesterday, you don't have to do the ICE table if you don't like it. Again, if you learned another way to do limiting reagent problems and you like doing it that way, perfectly fine. You could do that. You don't necessarily have to do the ICE table, but if you want to, you can. But you could choose any way you want to do it. That's a legitimate way, obviously, of doing it. So don't feel like you have to do it one way or the other. I really don't have a preference. Any questions on limiting reagents or sort of the different ways of doing it? I would just say the disadvantage to say the process that we just saw or some of the other processes is if you're asked questions like, how much of your excess reagents left over, you oftentimes will have to kind of go back and do some other calculations and stuff like that. It's not sort of everything set up for you as nice in the ICE table. All right. So why don't we try another one just to make sure everybody's working on the right spot here. So we got 100 grams of ammonia reacts with 100 grams of carbon dioxide, and it makes 120 grams of the NH2 2CO. What is the percent yield? So take some minutes here and work it out. Let me give you some numbers. We got carbon, that's 12.01. We got oxygen, which is 16. Nitrogen, 1401. And hydrogen, 1.008. All right, take a few minutes to see what you come up with, then we'll talk about it together. All right, so let's take a look and see how we're doing. So we have 100 grams of ammonia, which is here, reacts with 100 grams carbon dioxide, which is here, produces 120 grams of this guy here. So again, some key highlights here from what's given to us. We are given enough information for both of these guys to determine moles, which means that this definitely is a limiting reagent type problem. We're also given how much product here we'll make, and that is going to be our actual yield, which is given to us. And remember that our percent yield, which is ultimately what we're looking for, is our theoretical divided by the actual times 100%. So in terms of this, we already have the actual, which is usually the case in textbook problems, but we do in this case have to determine the theoretical yield. So this again really is a limiting reagent problem. And much like most any type of stoichiometry problems, we want to start with a balanced equation, which we have. We then want to convert each of our reactants into moles. So we'll do that here on this page. So we have 100 grams of ammonia. In order to do that right, we need to go to the periodic table and calculate the molar mass of ammonia. So that's 1 nitrogen at 1401 plus 3 hydrogens at 1.008 gives us 1703 grams per mole. The 1703 will go on the bottom so that the grams cancel. And that's going to get us 5.872, we'll call it. We're going to do the exact same thing for our other reactant, which is also 100 grams of CO2. We again would go to the periodic table and calculate the molar mass. You're right. It is. I think I said it right, but wrote it wrong. Thank you very much. I'm going to try that again. It is the actual divided by the theoretical. I think I might have said it right, but wrote it backwards. There we go. Thank you. It is actual divided by theoretical times 100. Thank you. So we'll go to the periodic table and do 12.01 plus 2 times 16, giving us 4401 grams per mole CO2. And if we do that, we're going to end up with 2.272 moles of CO2. Yes. So again, just to be clear, it is the actual divided by the theoretical times 100 per percent yield. All right. So now that we have this, we can solve for our limiting reagents. Again, I'm going to use the ice table approach so you can see it again. But if you choose some other way, we all should end up in the same spot. Just write the equation down here. Okay, so initially we're going to use the NH3 moles, which was 5.872, and our CO2, which was 2.272. And again, initially we're going to assume we have nothing of our products. The change part here, we're going to lose our reactant, so it's going to be minus 2x, again, the 2 for the coefficient, minus x, again, the coefficient for CO2 is 1. This is going to be plus on the product side, so plus x, coefficient is 1, and also plus x as the coefficient there is 1 as well. So at this point, we can go to our equilibrium step. We're going to carry those guys down, 5.872 minus 2x, 2.272 minus x, x, and x. Any questions on the table so far? So this is the part where we are going to determine which one is our limiting reagent. So what we want to do at this point is set each of these reactants equal to 0. So this one's very easy to solve. X would equal basically the same number. X in this case, we're basically going to divide it by 2. So that 5.872 divided by 2 gives us 2.936. And again, we're just solving for X when we set it equal to 0. So basically take the 2X to the other side and divide by 2 will get you there. We see that this number here is larger. So this is not going to be the number we're looking for. This one, again, is the smaller number. And again, what that means is the CO2 in this case would be our limiting reagent. By default, the excess reagent is going to be the NH3 in this case. Any questions on that? So as I mentioned before, the nice thing about that is that X that we just solved for is the moles for each of these things. So all these X's is this number. In this particular case, we're just interested really in this product. So what we see is that the moles of our product equals X, which in this case equals 2.272 moles of our product. We're not interested in just moles, but we want grams really for our theoretical yield, because our actual yield was in grams, so everybody's in the same unit. So the molar mass here of our product would be 2 times 1401 for the nitrogens, plus 4 times 1.008 for the hydrogens, plus 12.01 for the carbon, and 16 for our oxygen that's there. So the molar mass of this guy here from the periodic table is something like 60.06 grams per mole. So to finish up this part of the calculation, we're going to take 2.272 moles of our product. We're going to convert it into grams by multiplying by the molar mass. And what we will end up with is 136.5 of our product. And again, this is our theoretical yield. Any questions so far on that calculation? We won't do it this time, but again, just to remind you, if you want to figure out also how many grams or moles of water, you simply would put the X into here, and that would tell you that you produce 2.272 moles of water. You can multiply it by 1802 and figure out how many grams that would be. You also, like we've been talking about, can quickly put it into here, and that will allow you to figure out how many moles of your excess reagents left over. And then you can figure out, by using the molar mass to 1703, how many grams of the NH3 would be left over. So again, sort of the benefit is, you know, you could kind of pop this X value into everything. If you pop it into this last one, it should equal 0 about, right? Because that's the limiting reagent. But you could put it back into each of those things and relatively quickly answer, you know, all those type of questions. We still haven't really answered the question here because we're looking for the percent yield. So the last thing that we want to do is take the percent yield, and I'm going to try to write it right this time. It is going to be our actual divided by our theoretical times 100%. And the actual, again, was given in the problem, and I believe that was 120, if I'm not mistaken. That's 120 grams. And we calculated the theoretical being 136.5 grams times it by 100%. And we'll get something like 87.9%-ish. 87 point, let's see, use the actual numbers here. 87.91% as our percent yield. Not terrible, maybe not the greatest, but not horrible. Remember, percent yield, you know, you're shooting for, probably won't get 100%, but in that ballpark is, you know, pretty good. Obviously a very low percent yield, the reaction didn't go very well. Any questions on any of those steps? How to do limiting reagent problems, how to do stoichiometry problems. Obviously, you need to be able to do basic stoichiometry problems, limiting reagent problems, figure out percent yield, figure out excess reagent, how much is left over, and all that kind of stuff. Any questions on any of that? Okay. So I think that will do it for sort of stoichiometry. We're going to switch gears just a little bit here. We're going to talk about solutions, and we're also going to talk about sort of molarity, and we'll get back into some stoichiometry a little bit later on as well. So let's see here. It involves solution. And I'll just throw this on the screen in case you want to see it later. But this is, again, the other way that you could kind of do this problem. This is the way where we pick one of the reactants and try to find which one's the limiting reagent in that calculation. And in this case, you can see we come up with the same result. We needed 4.5 moles of NH3. We started with 5.87 moles of NH3. So we did have enough, and tells us the same thing, that the NH3 is our excess reagent, the CO2 is our limiting. And as you can see here, we do end up with the same answers as we got with the ice table. Again, it's just a preference, whichever way you want to do it. You might not have the slides, I don't think, to be honest with you. But if you want, you can see it on the video. Obviously, it'll be on there, so you can watch it there. All right, so let's talk a little bit about a solution. And a solution really is a homogeneous mixture. And if you remember, a homogeneous mixture is something that when you mix it, it looks the same throughout. And there's really two parts to a solution. There's the solute, which is the smaller part of the solution. And there's a larger part, which is the solvent. And solutions, just a reminder, is really those guys that end up with that aqueous symbol next to it. And a reminder that, again, the difference between aqueous and the L symbol, which is liquid, is when you have a liquid, that's something like just water by itself. And if you take something like sodium chloride, which is, say, is solid, and you mix these two together, the sodium chloride will dissolve in the water and will make a sodium chloride solution, which will get that aqueous symbol next to it. So in that example, for what we're talking about here, the sodium chloride would be considered the solute, and the solvent in that case would be water. Water is a solvent for a lot of things, not always everything, but it is a lot of things. And we'll talk in a later chapter why that is, because it's a very good solvent for certain things. But the easy way to figure out what the solute is for a solution, for example, is that the name of the solution is really what the solute is. So somebody says, I have a sodium chloride solution, then sodium chloride was the solute. If you have a hydrochloric acid solution, hydrochloric acid, right, was the solute in that particular case. So down there on the bottom are some examples of some solutions, soft drinks, water's the solvent, and then obviously there's a lot of other small things dissolved in it, right? Sugar, CO2, some other things that are dissolved. I can't really see it on my slide, but in the middle, I think it's air. And the larger component of air is nitrogen, while the other components of air, right, are things like oxygen and argon and other things, depending on where you are. Solder as well as lead is kind of the major component, and tin. So as odd as it may sound, and we usually think about sort of solutions as being sort of liquids, if you will, they can be gases and also solids as well. Not usually traditionally sort of thought of as solutions, but they technically are sort of mixtures of those things. So let's talk about some concentration of solutions, and the most sort of common concentration that we deal with is molarity, and molarity is moles per liter, and molarity, which is big M, is moles per liter. It technically is moles of solute over liters of solution. And you can use this like a formula. You can rearrange it and solve for any of those things. So if I wanted liters, it would equal the moles divided by the molarity. If I want moles, which is a very, very common conversion or calculation you do a lot in chemistry, is the liters times the molarity. So it's important that when we see something written like 4.5 big M sodium chloride, what that really means is that we have 4.50 moles of sodium chloride in a liter of solution. And when you do calculations, I highly recommend that you get rid of the big M and convert it into moles per liter. It's very, very common. People leave just the big M when they do the calculation, and they have no idea where the liters part should be, or forget about the liters part and stuff like that. So technically speaking, you could use it like a conversion factor. You could write it like that, or if you needed to, you could put the liters on top and kind of flip it and write it like this. The number always stays with the moles part, and it's always in 1 liter in terms of the molarity. So we can do some calculations that involve molarity. Let's take a look at one here, as I kind of wrote over it there. What is the mass of Ki required to make 500 milliliters of a 2.8 molar Ki solution? So why don't you take a second and see what you come up with. Let me just kind of erase some of that stuff that's kind of in the thing. There we go. All right, so why don't you take a second or two to see what you come up with, and then we'll talk about it just to make sure. Give you some information. Potassium is 3910. Iodide is 126.9. All right, take a moment and see what you come up with, and we'll talk about it. Okay, so we're looking for the mass here, which is usually grams of Ki that's required to make 500 milliliters of a 2.8 molar Ki solution. So again, here, if you sort of think about what's given to you, you have the molarity given to you. You have the volume given to you, not in liters, but in milliliters, but you essentially have that. So again, if you weren't sure where to go, solving for moles is probably the right approach. So we could use this method here. We do have to do a couple of conversions here. We do need to convert the milliliters into liters. So 500 milliliters divided by 1,000 gives us 0.5 liters. And again, when we have a number like this basically means that we have 2.8 moles of Ki per liter. Or again, you can use it in the opposite direction if you want to kind of use it as a conversion factor and sort of do dimensional analysis. So we'll do it that way. We'll kind of do the dimensional analysis way. We'll start with our 0.5 liters of Ki. Using our guy on the left there, that's going to give us 2.8 moles per liter of Ki. And if we do that, we will end up with 0.5 times 2.8 gives us 1.4 moles of Ki. Now, if we want to get grams, we're going to get the molar mass. So basically, we're just going to add these two together since it's one of each. So it's going to be 3910 plus 126.9, something like 166 grams per mole, again, coming from the periodic table. And that's going to get us something like 232 grams of Ki. Any questions on that calculation? Again, liters would cancel, moles would cancel, and we're left with grams. So basically that number means that if we wanted to make this solution, we basically would scoop out 232 grams of Ki. We would put it in probably enough water to make a total volume of 500 milliliters. Obviously the Ki would dissolve, and we mix it up really well. We would have a solution that has a molarity of 2.8 molar. Any questions on that there? All right, so let's try just a couple more here just to make sure. Where did I find that page I could use? I'll use this one. All right, so let's say we had, we want to know what is the molarity of a solution made by dissolving 12.01 grams of potassium nitrate in enough water to make, we'll do 10 milliliters of solution. All right, so give that a go. Give you some numbers. The potassium there is still 3910. Nitrogen 1401. And oxygen 16. All right, so figure out what the molarity is there and see what you come up with. Okay, so on this particular one here, we're going to be looking for the actual molarity, which again is moles per liter. And in this particular case, we are given really the liters part, again, not in liters, so we do have to do that conversion. We don't have the moles, but we do have the grams. So again, a very common conversion. We do need to convert those grams to moles. So our KNO3 would be 3910 plus 1401 plus our 3 times 16 from the periodic table. And it looks like if you do that for the molar mass of KNO3, you will end up with 101.1, looks like. So we're going to use that to convert into moles. So we'll take the grams of it that was given to us. We will convert it into moles by taking 101.1 grams per mole. Gives us 0.1188, we'll call it 0.1188 moles of Ki. We now have the top part. So to get the molarity, it would be our 0.1188 moles divided by our volume converted to liters. So we're going to divide it by 1,000, or you could just move the decimal point 3 places to the left there. And that would get us 11.88. And the answer here in terms of units is you can leave it as moles per liter, or you could say 11.88 and write the big M. So you could do it, obviously, either way is perfectly fine. Any question on that calculation? Now, when we talk about molarity, like I said, when you're doing calculations, I would get rid of the big M and use the moles per liter so you could clearly see all of the liters and stuff like that. Yeah, sig fig wise, good question. Sig fig wise actually should probably be 11.9 based off of that. Thank you. So since we did have that, which is technically 3, this guy would be 4. So this guy technically should have the extra 0 there. And so sig fig wise, it should be more like this. Thank you. And that would be based off of taking 4 divided by 3. So when we look at molarity and concentration, and especially with ions, there is a way that we relate molarity basically to its concentration. So for example, in this particular one here, we'll use the correct sig figs here, which should be 11.9. If we had 11.9 molar KNO3, and we were interested maybe in just the molarity of the potassium ion or the nitrate ion, for example. When we take something like potassium nitrate and it breaks apart into a potassium ion and a nitrate ion, right? And if the concentration of this guy is 11.9 molar, the concentration of just the potassium ion would also be 11.9 molar, and the concentration of the nitrate ion would also be 11.9 molar. And the reason for that is kind of like stoichiometry. It's a 1-to-1 relationship between those two. It's also a 1-to-1 relationship between the nitrate, which means the concentration of each of those ions individually would also be 11.9 molar. Obviously, it's not additive, so if you add this up, you don't get 11.9, but is concentration of each of those. And the reason really, why that is, as opposed to say you had something like, let's do 0.1 molar potassium sulfate. No, minus potassium sulfate. When it breaks apart, in this case, we get 2 potassiums and a sulfate ion. And if we were interested in just the concentration of the ions, if this guy was 0.1 molar, the potassium is now a 1-to-2 relationship, which means the concentration would be 2 times 0.1 molar, which would give you 0.2 molar for our potassium. But between the whole thing and sulfate, it's a 1-to-1 relationship, which means the concentration of just the sulfate ion would be 0.1 molar. So basically, it's like twice as concentrated, right? In terms of potassium ions. So when that breaks apart, you get twice as much potassium ions floating around, which means that it is twice as concentrated, and the molarity would double, while the sulfate is basically 1-to-1 relationship, so you get the same thing. So if an ion breaks apart into, say, a 1-to-3 relationship, you would multiply the concentration by 3, 1-to-2 relationship, multiply it by 2. The reason really why that is like that and how come it comes out like that is, I'll borrow this page. So we were doing 0.1 molar potassium sulfate. And again, when that potassium sulfate breaks apart, like we just saw, we get this deal. And if you really did sort of the long calculation to see how come this becomes doubled, the long calculation would be like this. You would take the 0.1 moles of the whole thing divided by liters, right? So that is the molarity, what we started with. And now what we could do, just like in stoichiometry, it's a 1 mole of K2SO4 gives you 2 moles of potassium, which means when we do that conversion, for every 1 mole of the whole thing, you get 2 moles of just the potassium ion. The moles of the whole thing cancels, and you're now left with moles of potassium over liters, which is the molarity of just the potassium ion. And essentially you get, as you can see, the same number as we just got on the previous slide by doing it the long way. Essentially all we did is, like I said, multiply by 2. Now, if you do the same thing for our sulfate, this is why our sulfate will end up the same number, because for every 1 mole of the whole thing, there is 1 mole of sulfate. It's a 1-to-1 relationship, right, from the equation here. And that means when you do your little stoichiometry sort of calculation, 1 mole of the whole thing gives us 1 mole of just the sulfate, basically a 1-to-1 relationship, and we see that we end up with the same concentration. So that's why I say if it breaks apart into a 1-to-2 or 1-to-3, you really could just multiply by 2, multiply by 3. This is really the long way to get to that answer. The short way is to just simply take the coefficient and multiply by the concentration. So sometimes in problems, you may not be interested in necessarily the whole thing, especially in an ionic solution. You may be interested in the concentration of one of the ions, the positive ion or the negative ion. And you could kind of do almost like a stoichiometry relationship, which is really what we see here on this screen, to figure out the concentration of not the entire guy, but maybe just one of the ions that are floating around in that solution. Any questions on sort of that relationship there? Okay, or any questions on molarity in general? Go back to where we were. Okay. So this is one way that you can make a solution. For example, might be hard to see on my screen, it kind of is, but this is a volumetric flask. Volumetric flask has basically one marking, and that marking is basically the volume of that flask. Whenever you use anything that's volumetric, typically it's, to 2 decimal places. So you can see they have some solid in the bottom there. They're going to add a little bit of water or solvent to it, going to get it to start to mix and dissolve. Usually you want to wait until you get most of that dissolved before you kind of bring it up above the line there. or to the line, not above the line, but there's sort of where the neck of the flask starts. So usually you want to keep it in the larger part, gives you a little bit more area to mix it and stuff to get that stuff to dissolve. Once you got it pretty much dissolved, you want to carefully bring it up to the line where the bottom of the meniscus is at that line. This is a case where you do not want to go over that line. And if you do go over that line, that's not good because it's already mixed, right? So very common people kind of mess up, like instead of stopping here, they go in the upcoming titration experiment, which I guess the good news is you're not going to physically do it and have this happen to you. But people go, oh, I kind of overshot the line there a little bit, or in a lot of cases, a little bit. I way overshot the line hopefully not that much, but they overshoot the line. They go, can I just like pour out some into the line? Is that okay? And as you may imagine, you can see you started with solid, that solid dissolves. So if you pour out some of that excess, if you go over the line, you're not only just pouring out what you envisioned the water part, but you're getting rid of some of the solute that's in there, right? And obviously you won't have the correct concentration. So I guess a benefit of not having to do the titration experiment in person is that won't happen to you. You won't go way above the line or anything like that. So whenever you use these sort of volumetric flasks, you do want to always kind of, usually good practices, you kind of get it to dissolve down here. You could be pretty liberal with like a wash bottle and some water. Then as you get kind of close to that line, usually, you want to use like some type of dropper or something like that to really, dial it in to get the water solution up to that line. All right, so let's talk a little bit about dilution. And dilution is a process where we take a solution that is more concentrated. Sometimes solutions are referred to as stock solutions as being pretty concentrated. And we basically add more solvent. And the process of adding more solvent, a lot of times is we think about it as adding more water. Again, a reminder that water is not always the solvent that's used 100% of the time, but it's used a lot of times. So we typically will add more solvent to it, and the molarity will get less. So it's kind of like the situation if you get a big drink, right, from a soda fountain, right, and you put ice in it, right, you go to class and you leave it in your car. By the time you're done with your classes, you come out, all the ice is melted. And obviously that soda is no longer as strong as it was before, right? It's become very diluted by all that water that basically was added from the ice cubes that melt. You still drink it, right? Because, how bad could it be sitting there for 4 hours, right? And then you regret it probably afterwards. But that is sort of the process of dilution. So what does that really mean in terms of what happens to the concentration or the molarity? Well, if we think about molarity, which is technically moles of solute over liters of solution. When we do some type of dilution where we add more water to it, the number that we're actually increasing is the bottom number here. So we're making the volume or liters of solution a larger number. So as that number goes up on the bottom, that means my molarity goes down overall, right? Because we're now taking a small number divided by a larger number. So the molarity will drop down. So typically the process of dilution will lower the concentration. And again, when we do a dilution, the important part is the moles of the solute before and after remain the same. So that doesn't change. There is still, for example, I think if we count the circles here, these are our solute particles. There's 3, 6, 9, we got there 12, 15, 18. You come this way, you got 4, 8, 12, and all the same numbers, hopefully around there. But you have basically the same number of circles on each side. The only difference is we added more water. So the important part of dilution is that the moles of solute before the dilution will equal the moles of the solute after the dilution. So it doesn't change. We're just changing the volume, which brings down, again, that concentration. So we have a dilution equation, which most people use as M1V1 equals M2V2 because technically molarity is the most common unit of concentration. This is usually before the dilution, your more concentrated part. This is after your more dilute part, the twos. In reality, it doesn't matter as long as you keep the numbers correct on each side. You will sometimes see this dilution equation written as C1V1 equals C2V2. It basically is the same. C in that one is just a generic term for concentration. Although most of the time we use molarity as the concentration, it doesn't have to be. So, for example, we'll talk about in this chapter as well some other concentration units, things like, for example, percent mass to mass, percent mass to volume. You could use those in this formula as well. But most people use the M1V1 equals M2V2 again because molarity is typically what is usually used in terms of concentration. So why don't you calculate this and see what you come up with? How would we prepare 60 milliliters of a 0.2 molar nitric acid solution from a stock solution that is 4 molar? So take a minute or two and see what you come up with. Okay, so let's talk about what's going on here. So we're obviously doing a dilution here. And again, we're not doing any type of reaction because we're taking nitric acid. We have nitric acid. So this everybody's clear about sort of what is going on. We basically have a bottle sitting there, right? That is 4 molar of some nitric acid here. And basically what we want to do is make a another solution over here that has a molarity of 0.2 molar, and we want to make a total volume of 60 milliliters. Now, 4 molar, which is a larger number, and when you do have molarity, right, the bigger the number that comes in front of the M, the more concentrated it is, right? So that bigger the number, the stronger it is, the more concentrated it is. So we have basically, if we think about it, we have M1, which is 4 molar. V1 we don't have. We do have M2, which is our goal here of what we want to solve, and V2, which is 60 milliliters. So we can use the dilution equation here to figure out what we need to do. And again, in this case, M1 V1 would equal M2 V2. In this case, we're solving for V1 as we don't have it, which would be M2 V2 over M1. Putting in our numbers here, we do get 0.2 molar times V2, which is 60 milliliters, divided by 4 molar. Now you may ask yourself, I thought you had to convert liters, right, times molarity. And normally you do, but in this particular formula, because we are dividing by molarity as well, the molarities will cancel and we will be left with milliliters. So if we do that, we do end up with 3 milliliters. So what does that 3 milliliters really mean? What that 3 milliliters really means is that is how much of the more concentrated solution I need to take out. So basically what I'm going to do to make this solution is I'm going to take out from here and put into here 3 milliliters of that solution. The rest of that solution is going to be water, right? I'm going to fill the rest up with water. So the question is, do I fill the rest up with 60 milliliters of water? So do I top the rest of this off now with 60 milliliters of water? And the answer is no, because you would not want to do that, because if you did that, you would take 60 milliliters and 3 milliliters, you would end up with 63 milliliters of a solution. And that is too much, right? So a very common question that's asked in dilution problems is, how much water should you add? So I've already put in there 3 milliliters. I want a total volume of 60. So usually to find out the volume of water, which is a very common question, you usually take volume, the second volume minus the first volume. And that in this case would be 60 minus 3, which means I need to put in there really 57 milliliters of water. So our 57 milliliters of water plus our 3 milliliters of the nitric acid gives us a grand total of 60 milliliters, which is what we're shooting for. And if I mix this up really well, it will apparently turn red. And I will have a solution that now has a concentration of 0.2 molar and 60 milliliters. So a very common dilution type question is just that. They ask basically how much water would you add to make this solution? And typically speaking, volume 2 minus volume 1 would get you your volume of water or volume of solvent that needs to be added. Questions on that? So just to clarify here in terms of this part and what's happening when you do something like taking the molarity times, and we'll do it here maybe. When you take molarity, which is technically molarity times milliliters. Now, if you do that, which you can do that, the only difference is what you get out is not moles, but you get what is known as millimoles. And if you take millimoles and you divide it by milliliters, the millis will cancel out and get you back to moles per liter. And that's really what's happening here and why we don't have to convert it back to liters here in this particular case, because it will work out okay in that case when we multiply that, because technically speaking, molarity, although most people don't consider molarity this or think about it this way, molarity is millimoles over milliliters. Again, when you get rid of the milli part of that, you're back to moles per liter, which is typically what people think about in molarity. And that's why in this situation, if you're multiplying by milliliters and then going to be dividing by either milliliters or molarity or something like that, it will all come out okay. And just to be clear though, if you are straight up doing a problem where all you have is molarity and the volume, you do need to make sure it's in liters, because in most cases you're looking for moles and not millimoles like what you would get if you took molarity times milliliters. So it is technically okay to multiply by milliliters, but what you have to remember though, if you multiply the molarity by the milliliters, is you're not getting straight moles. You're actually getting what are known as millimoles. So if you don't do the conversion correctly at the end, you're going to be off by that factor of 1,000. So that's why most people, when they sort of taught this or learned this, it's always sort of drilled into everybody's head, convert it to liters, because that usually is what you're looking for, is moles is usually what you're looking for. And that way you'll be in the right unit. But, you know, technically speaking, it's not illegal to multiply milliliters by molarity. The only difference is, again, you don't get moles, you get millimoles. And if you don't do some conversions in most problems, like I said, you'll be off by that factor. Any question on dilutions, molarity, or any of those type of things? All right, so I think this is a good stopping place actually to stop before we continue on. So we'll stop here for lecture today. We have lab again. Hopefully all the time is right there. I apologize. It's weird conference Zoom. They did some weird thing with the time when you set it the right time, and then it changes to like universal time or something like that. I don't know. But always, just so you know, if you ever have a trouble going through that sort of conference Zoom link, you could always go to the module sections in that announcement like I put out there. And those should always have sort of the right link. That should definitely work for sure. It won't be changed or anything like that. So always check that module section if for some reason the other one is not working for you and stuff like that. All right, so today, like I said, we moved everything sort of back. So today, the study assignment is going to be due at the end of lab, and then we're going to start the next experiment, which is experiment 9, I believe, and that also is about redox. So kind of the same stuff we've been talking about in lab yesterday and the last couple of days and stuff like that. So we'll see everybody in about 20 minutes or so. Make sure you put here if you haven't done so already, and I'll see you in 20.